Let's begin. Yeah, hello, good afternoon, and welcome to day two of UK Hydrogen Week here at Brunel University. For those of you who missed yesterday's episode, this is the second in a webinar series titled Thinking Differently in Hydrogen, hosted by me, Brunel's Royal Society Entrepreneur in Residence, Alexander Reek. Each day we will be having a presentation from a Brunel expert on a specific topic, followed by a talk from an SME who are developing technology to help support the growth of the UK hydrogen economy. Before we start, a couple of housekeeping points. Firstly, these webinars will be recorded, so if anyone has an issue with that, then please leave. And then once the entire sort of 5-episode series has finished, we will be putting them on the Brunel YouTube channel, so you'll be able to find them again in case you did miss any that you wanted to see. After the talks, like yesterday, we'll be having a Q&A session, so please do type your questions into the chat function, or you can put your hand up during the Q&A session and I'll endeavour to get round to you so you can actually ask it in person. And finally, please do keep yourself muted for all the talks, just so that we can sort of focus on that and then we can ask questions later on. So yesterday we had two great talks on hydrogen living labs and then had a great and very interesting discussion afterwards. One of the discussion points that was raised was the issue of electrification of the transport sector in the UK. And this moves very nicely onto today's topic, which is hydrogen combustion. Now, for those of you who know, hydrogen and related fuels such as ammonia and methanol are being considered as one of the ways in which we can decarbonise transport. And yesterday we discussed how hydrogen is more beneficial for larger vehicles, such as large trucks in marine areas and even aerospace applications, compared to for consumer vehicles, which are now very much more electrified than they are hydrogen. And so today we'll be hearing from two people who are sort of working on the combustion side, two different angles as well. So firstly, Dr. Xinyan Wang from Brunel, who's going to be looking at it from an internal combustion perspective, and then Dr. Michael Goodisman from Lifting Gas Limited, who's actually looking at it in some ways the opposite way to reduce the effect of combustion so that hydrogen can be used in airships. So first, I'll give the floor to Dr. Xinyan Wang, who's currently the UKRI Future Leaders Fellow at the Centre for Advanced Powertrain and Fuels at Brunel University London, and has a focus on advanced renewable fuels, multi-fuel combustion engines, and integrated engine generators for a future low-carbon transport. So the floor is yours.
Thank you, Alex, for your kind introduction, and thank you very much for giving me this opportunity to present in this very interesting event. So my name is Xinyan Wang. I'm currently UKI Future Leaders Fellow on Advanced Powertrain System and Fuels. So today I would like to share some experience on our research progress on hydrogen-powered zero-emission engines for future transport. So before I start my presentation, I'd like to give a brief introduction of the Center for Advanced Powertrain and Fuels at Brunel. So as one of the largest combustion engine and fuels research group in the UK or even in Europe, basically the center covers a wide range of engine research and fuels. Also, in recent years, basically with the trend on zero carbon emission propulsion system, we are moving from fossil fuels to future fuels, including hydrogen, ammonia, alcohol fuels, and e-fuels. So in our research center, we do have a lot of research facility, from thermodynamic engine testing facility. For example, here I show a few examples, the light duty engines, here another one. And recently on this one, we just tested pure hydrogen combustion engine. So also we cover some other heavy duty engines. For example, this one is a 2-liter heavy duty compression ignition engine. And we have done significant work on dual fuel, including by using the alcohol fuels, methanol, ethanol, and recently methane, hythane, which includes the hydrogen. And in addition to these thermodynamic engine, we have other optical research tools, for example, optical engine. And here we have some optical images from high pressure injection, as well as a subsequent combustion process. In addition to these experimental tools, we have the access to UK HPC facilities so that we can perform advanced simulation studies. For example, here I just show engine combustion process. And in last 20 years, the center has published 5 books on advanced engine technologies, engine instrument, and laser diagnostics. So this is the outline of my talk. So first part will be the challenges and opportunities of moving towards net zero. So this graph showed the global temperature change since 1850. And obviously the blue color indicates lower temperature and the red color indicates higher global temperature. So it is visible that we do have global warming effect. So basically we can see in recent 20 or 30 years, the temperature increased significantly. So when we look at the carbon emission profile from, let's say, 200 years from now, and it is visible that in recent 100 years, the carbon emissions has exponentially increased. And obviously, there are close relationship between global warming and the carbon emissions. So we do need to address the challenge of carbon emissions. And in the UK, from 1990, we do see carbon emissions gradually reduce. And the UK government also set a stringent target for carbon reduction. For example, by 2030, we have to reduce carbon emission by around 70%, and by 2075, around 80%. By 2050, we have to achieve net zero. So they are all very, ambitious target, but it's not very easy to decarbonize, in particular for transport sector. So the left graph showed the carbon footprint of UK citizen. Obviously, the green color indicates the travel sector, and currently around 27% basically carbon emissions are from transport sector in the UK. And obviously, we can use different transportation propulsion system to reduce carbon emissions. And the right graph showed the sale of light duty or passenger vehicles in the UK in 2021. And obviously, you can see the petrol and the diesel powered vehicles shows significant decrease. And the hybrid vehicle, here's a mild hybrid, and also the pure electric vehicle, plug-in, and the other form of hybrid has significant increase in last few years. But when we consider or when we calculate the percentage of the vehicles with engine, because for hybrid vehicles, it does have an engine. So around 88% of the vehicles still have the combustion engines. And for these heavy duty sector, for example, truck or long haul vehicle, for example, aviation, marine, and for some special application, remote, for example, the remote agriculture vehicles and mining or other machinery vehicles, these sectors will be even difficult to be electrified. So we do need to see options to decarbonize. So if I summarize the scenario, different propulsion system into this graph, so we'll be able to see for the short term, obviously, we do have these alternative solutions, for example, hydrogen fuel cell or battery electric vehicle. But currently, the market share is still low, which means it can only deliver very limited carbon reduction potential. And for long term, for example, hydrogen fuel cell is still promising, but there are limited applications. For example, when you need a relatively higher power density, for example, aviation or even marine, and there will be very limited application of these alternative solutions. But we can't rely on fossil fuel engines because they do have higher carbon emissions. So we need to find out our solutions. First, can we find any short-term solution and a long-term solution for heavy-duty and long-haul vehicles? And secondly, is it possible we can borrow something from the hydrogen fuel cell or battery electric system to bridging the gap and to deliver a faster carbon reductions? And I do think we do have some solutions here. So if we look at the fuel cell, obviously it uses hydrogen-based fuel, no matter it's pure hydrogen or ammonia or methanol derived from hydrogen. It does have the zero carbon fuel, hydrogen. And secondly, from the electric vehicle, obviously it has very high efficient electric motor generator. So if we combine all the system together, we may have a sweet point here. Basically, it integrates all the existing technologies. For example, using hydrogen in combustion engine, also integrated the electric system to further improve the system efficiency. And basically, that's the starting point of the hydrogen or alternative zero carbon fuel combustion engines. So the second part will be the advantages of hydrogen combustion engine. So first, I would say it is a net zero solution. And if we use this renewable energy, no matter it is come from the wind power or solar power, we'll be able to use that renewable energy to split the water by electrolysis to produce hydrogen. Then they can be stored and distributed for industrial usage or transportation. Obviously, we can use combustion engine technologies or fuel cell technology, but while we also look at the hydrogen combustion engine, there are several advantages. First, carbon emission, obviously it is zero if we have the energy from the renewable source. And secondly, I think it is quite important point. So combustion engine can use low purity hydrogen, which means we can reduce the hydrogen production cost. And also, we can make use of existing engine technologies and also the hybrid electric system to further reduce the cost of the engine itself. And also, if we look at the efficiency, actually, we can directly put hydrogen into any existing engine, but obviously we need to do modification to have a better efficiency. But by slightly modifying current engine, we'll be able to achieve decent efficiency. If we integrate more advanced engine technology, we'll be able to further increase the engine efficiency, which is equivalent to fuel cell efficiency. And in terms of the performance, obviously it is a transient machine which can accommodate instant cold start and shutdown. So it's just like a typical combustion engine. It doesn't need to have significant time to warm up or complicated shutting down procedure. And in terms of pollutant emission, which is one of the most concerns, would be the NOx emission, but by using advanced engine technologies, for example, lean burn, we'll be able to reduce NOx emissions almost towards zero. And the durability will be more or less like the typical combustion engine, so there's no any issue with that. And in terms of the social and economic impact, obviously we can make use of existing engine infrastructure, engine production lines, and also we can maintain the employment of the engineer in combustion engine. So in addition to the engine manufacture cost, another important cost would be the total cost of ownership. So here is an estimate from AVL, and basically the calculation is based on the 5 years usage and with mileage around 600,000 kilometer. So here we compare three technologies: the baseline diesel and hydrogen combustion engine technology and the fuel cell vehicles. So we'll be able to see the total cost of ownership over 5 years. For hydrogen, it is almost half of the fuel cell electric vehicle. So it is quite promising because it is a cost-effective solution, which means we can quickly implement this technology into the market, and also this will deliver a fast CO2 reduction. So here, I would like to talk about the hydrogen combustion engine technologies. As mentioned, even for existing engine, if we put hydrogen into the engine, we'll be able to burn hydrogen, but it doesn't really guarantee a high efficiency combustion. So what we are looking here is how to improve the engine efficiency by considering the difference of the fuel properties. So this table shows the laminar flame speed of different fuels. So for hydrogen, it is around 290 centimeter per second, which is significantly faster than other fuel. For example, methane is around 40 centimeter, and for fossil fuel, for example, gasoline is in a similar range. So another important fact is flammable limit for hydrogen is quite wide. It can burn from 5% to 75%. And also, the ignition energy for hydrogen is minimal, is less than 0.02 megajoule, compared to the methane is around 0.3 megajoule. This very unique property can pose some problem when we look at when we design the hydrogen engine. First, for example, the lower ignition energy can lead to some backfire, which is dangerous. And also the fast flame speed can also produce excessive combustion, which can damage the engine as well. So when we when we design or research and develop the engine, we need to look at these properties and optimize the engine technologies to accommodate these properties. So the first point I want to discuss would be the hydrogen injection method. So obviously we can make use of existing engine architecture. So we just add one pot fuel injector to provide the fuel to the combustion engine, then to burn the combustion engine inside. But obviously there are some disadvantages. For example, we have limited power output because the added hydrogen would displace the fresh intake air, which means we'll have less intake flow. This will limit the peak engine performance. And also, there are hydrogen potential left in the intake port. We will have a backfire into the intake port. It can be dangerous. Alternatively, we can make use of the direct injection. So here is a schematic of that, of the direct injector. So we just add the injector to the cylinder. So we provide the fuel directly into the chamber so that avoids any hydrogen in the intake system. This can avoid backfire, and also it doesn't displace any fresh air. In this sense, we can increase the engine power performance. But this also means we have to make significant modification to the engine. It will add the cost. Similarly, another approach in relates to the gasoline type. We can make use of diesel type. In this case, we can make use of the pilot injection of diesel to have some ignition source to ignite the mixture from the pot fuel injected hydrogen. And we have done a lot of work, as mentioned, on the dual fuel ignited hydrogen mixture. And in addition to the fuel supply, and another important aspect would be the combustion mixture preparation. And we can operate the engine at a stoichiometric condition. In this sense, we can make use of existing after-treatment system to reduce NOx emission. And it does have better engine power performance and better transient operation condition. But alternatively, we can run the engine at lean condition. In that sense, we can increase the engine efficiency, and also the lean burn would significantly reduce NOx emission. And this is the results from Bosch. And we can see if we run lambda 1, basically the stoichiometric condition, NOx emissions are quite high. But when we run lean, basically the NOx emission at low load condition almost zero. and it will start to increase at a higher level, but it's still quite lower than the stoichiometric condition. And also, if we look at the efficiency, it is much higher than the stoichiometric condition. So I think I will briefly talk about the combustion, hydrogen combustion in this talk. And here I'd like to summarize my talk. Hydrogen combustion engines can make use of existing engine technologies and have less requirement on hydrogen purity. Therefore, can be an important solution for carbon reduction in transport sector. Although the direct usage of hydrogen in existing combustion engines are viable, in short term, the further research and development of dedicated hydrogen engines with ultra-high efficiency and zero emission is vital for its wider applications in a range of applications. With strong support by the UK RI, industry and Brunel University since 2020, the center has been very active in the R&D work on hydrogen combustion engine technologies through a number of techniques. Yeah, I think I'll finish here. Thank you very much.
Wonderful, thanks, Xinyan. I think it's really interesting to sort of see, especially in a time where we're really always looking for sort of a circular economy approach to be able to keep recycling and reusing things, that we can sort of use these kind of developments to take technology we've been using for a while and let it go for that little bit longer, rather than just throw it away and have to get in completely new. So I think that's fantastic. Thank you very much.
Yeah, thank you.
So next, we'll do some Q&A afterwards, as I said. But yeah, for the next talk, we're also joined by Michael Goodisman, CEO of Lifting Gas, who are pursuing the safe use of hydrogen as a lifting gas in airships through design and development of a thin film flame arrestor innovations. So Michael is the founder and CEO of Lifting Gas and is an aeronautical engineer with 12 years in the aerospace OEM, engineering consultancy and R&D roles, followed by 23 years in business development for a project cargo airline. Michael, the floor is yours.
Thank you for allowing me some time to present the activities of Lifting Gas Limited. Let's see if we can get this to full screen. How's that?
Perfect.
Okay. So, well, Lifting Gas is a UK registered company, and we're pursuing the safer use of hydrogen as a lifting gas in airships. Why would we take up such a challenge? Is it worthwhile? Well, airships are very strong when it comes to remote area challenges and project cargo and a number of other advantages, but focusing first of all on remote area challenges. Projects and communities in remote areas require general cargo, project cargo, that's outsized pieces, power and potable water. And there can be complications if there are poor road links, for example. In the situations such as a disaster, then what normally happens by air is large aeroplanes will fly to airports fairly nearby, transfer their cargo to helicopters, and the helicopters will carry lower payloads to the remote areas. These airports can become bottlenecks with this sudden increase in activity. Helium airships can fly large payloads directly to remote areas. However, hydrogen airships could also deliver hydrogen from the lifting gas itself. And from that hydrogen, you can get locally power and water. However, and this is the focus of our work, the hydrogen must be made safe enough to use. So our innovation is creating flame-resistant regions within hydrogen airships. Now, whether it's our solution or another solution, a hydrogen-powered airship, a hydrogen lifting gas airship can create a chain of advantages. So it would fly directly to the remote area. It would deliver general cargo, project cargo, and hydrogen. The hydrogen can be used as a fuel for a hydrogen power unit. An engine power unit can run on lower purity hydrogen. A fuel cell power unit needs very high purity hydrogen. So hydrogen from an airship envelope would need some sort of purification if that was the case. But in terms of the water that can be recovered from the power exhaust unit, water from an engine power unit is suitable for washing, but not drinking. Water from an exhaust of a fuel cell power unit can be suitable for drinking. I believe studies have been done on PEM, fuel cell power units, and drinking water. So putting a few numbers on this, if we take a scenario where an airship flies and delivers cargo to a remote area, and this is very important just for simplicity of this example, and the airship flies back empty, then you have the opportunity to offload the cargo and offload some of the hydrogen. For every 13 tons of cargo offloaded, you can offload 1 ton of hydrogen. And from every 1 ton of hydrogen, you can recover from the power unit up to 9 tons of water. That's the other 8 tons just coming from oxygen in the air at the remote area. You haven't had to carry that. Comparing helium and hydrogen, therefore, you can have a cargo airship designed for 150 tons, and it would deliver the 150 tons and come back empty. That's the helium airship. The hydrogen airship would deliver something like 100 tons to 130 tons. That's a weight penalty to make the system safe. It would, and I'll come back a little bit later why I'm talking about a range there. That would result in hydrogen of 7.7 tons to 10 tons being offloaded, 70 to 90 tons of water, and then resulting in a sort of useful delivery of, in effect, 177 to 230 tons. What's also very interesting, a natural advantage is for airships carrying hydrogen, is that you're carrying it at 1 bar pressure. So you don't have to compress it and have heavy containment material for compressed hydrogen. 1 ton of compressed hydrogen, when it's being trucked at 350 bar, needs 15 tons of container material. That's the ratio of the hydrogen to the containment material. Or if you've liquefied hydrogen and you've used a lot of energy to liquefy the hydrogen in the first place, but in addition to that, 1 ton of liquefied hydrogen needs 5 tons of container material. Again, both of those scenarios, we're not carrying such container material. We're doubling up on delivering cargo and delivering hydrogen. Very quick example from the previous slide, I mentioned up to 10 tons from that example. And just to give a sort of a feel for what that 10 tons gives you, it can power a hydrogen engine power unit for 53 days with an output of 115 kilowatts of electrical power. That's a few figures just below on how much that could serve in different countries, just based on some statistics that are available. Or another way to look at it is that's enough hydrogen to refill a car's hydrogen fuel tank nearly 1,800 times. So it's a sizable amount to take to a remote area. And again, just to illustrate what that hydrogen can give you. In terms of the water recovered, well, you get, as I mentioned, 90 tons of water, that's 90,000 litres. In an emergency situation, that's enough to maintain enough water for between 113 and 226 people. And that's based on 1 flight every 53 days for that particular airship. So again, it has a few benefits there. Okay, moving now on to the technology itself. The flame arresters in pipes are well established and too heavy to be used for airship purposes. So why can we consider flame arresters, thin flame arresters, this is what our technology is based on, for airships? And there's various reasons, but one of the core reasons is all to do with the flame speed. A faster moving flame needs a longer passageway to travel through a flame arrestor to allow that flame arrestor time to extract heat from the flame. So you can see there's 1,300, nearly 1.3, 1.4 kilometers per second in this particular experiment, and that was measured over only 4 meters from the ignition point. That was a quasi-detonation, and with a lower richness of the hydrogen, that turned into fast flames, still going very fast, 500 to 600 meters per second. That's why typical flame arresters for deflagration will be at least 20 millimeters passageway length and longer. So what happens if you have, and that's a confined flame. That's very important to stress that. That's pretty much confined in that tube. What happens if you have an unconfined flame? Well, an experiment was done, a large-scale experiment in Germany in 1983, and it was with 29% hydrogen. And again, the same distance, 4 meters, but in this case, the flame speed, 4 meters, was only 40 meters per second. And measured further out at 16 meters, it rose to 80 meters per second. So that unconfined nature provides an opportunity to consider thin meshes to act as flame arresters for airships. That's one important factor. It's not easy by any means, because that's still pretty fast flame, but it's something that might be achievable, and that's what we're pursuing. So essentially what we're talking about is constructing cells within an airship's envelope. On the left-hand side, you can see a cell made of a top panel and 4 side panels, and the 5th side is made of an envelope, of the envelope of the airship itself. Very thin mesh cells, less than 1 millimeter thick, and on each panel you can have, let's say, 1 or 2 mesh layers together. There's various reasons for that. It's a more conservative design if you've got 2 mesh layers instead of 1 mesh layer. The panels are connected together to form a continuous structure around the inside of an airship's envelope, so that for a non-rigid airship, you see these mesh panels. The dimensions of the mesh panels can be 3 meters by 3 meters by 2 meters, 2 meters being the sidewall, creating a 2 meter thick combustion resistant region around the inside surface of an airship's envelope. So that if there's a tear in the envelope and some air mixes with the hydrogen, and there's a static and there's a combustion, the combustion will be contained inside 1 or maybe a few cells, depending on the nature of the combustion. And most importantly, the central volume of the lifting gas will be protected from the flame. It's less likely to combust. For a rigid airships with multi-cells, it's a similar type of approach. Again, I'm not showing the framework here of the rigid airship, but you can provide a similar structure there, a mesh arrangement performing a similar function. The mesh layer, as I mentioned, weighs a significant amount, but that's offset by the fact you're using hydrogen to some degree, and you get additional buoyancy. So what this graph is showing is essentially the larger the airship, the higher the larger the volume of the envelope of an airship, the higher the maximum payload of that particular airship. And it shows a comparison of just using helium on its own, together with replacing the helium with hydrogen and either 1 mesh layer or 2 mesh layers. And basically, this is highlighting the fact that this design is suitable for larger airships. There's a lower percentage reduction of payload when you get to larger airships. So our research outline really is an airship. At the moment, there is a patent pending status for the airship flame innovation. Brunel are kindly collaborating with us. We're just about to start a CFD study of this. That will be followed by a 3-year research program, laboratory-based, using a test rig which has already been designed. And essentially we'll be testing small samples of meshes and perforated plates one of the interesting and very useful features of this small test rig is that you can control the flame speed. That comes in very handy when you're trying to study this. Should that prove successful, we can move to outdoor testing of mesh cells, maybe 1 meter by 1 meter by 1 meter, and then slightly larger and then slightly larger to see how they perform. And should that progress further, we will end up with airship integration testing. That's the presentation. Thank you.
Thank you very much, Michael. It's really interesting to sort of to see what's going on in that, because we've seen lots in the news about helium airships and just the worry about the sheer amount of helium you need when it needs to be used for so many other, in some ways, important applications. So yeah, it's good to see that there's more work going on the hydrogen side.